Well, good evening. I'm Charles Schultz, and this is the Randomizer. And tonight we're going to look at an unusual term. I say that a lot, all of them are unusual. We're going to look at the term autoionization. Now, this is something that we don't think about a lot. We always think about chemical compounds being stable, unchanging. They just sit there in a bottle of liquid or whatever. But in reality, there are changes occurring in molecules and their structures and how they act all the time. And this can radically change how they work. And things will happen that normal theory doesn't predict. So we're going to have a look at autoionization, what sorts of compounds do it, and why it's important. Meanwhile, I'm going to encourage everyone to go to universeciencecenter.com or schultzlaboratories.com and click through to our membership page, sign up as a member, and support the growth and addition of new rooms, new exhibits, and interactive materials on our website. Our virtual learning world is open to people from all over the world, and we also are hoping that we can get more members to help us improve the content. If you're an educator or even self-educated and you wish to share your works or your teaching with people around the world, contact us and we can set up a virtual gallery or classroom for you to use where you can both display some of your works in the gallery and entertain students and teach them in your classroom. That's a great thing. It's a win for all of us, and it helps everybody get more familiar with this medium, virtual learning and teaching. Meanwhile, we have our robotics classes started up again Monday evenings at 9 p.m. Eastern Standard Time, and we will have one tonight. So join us at 9 p.m., and I think you're going to learn some things you never imagined about robotics. We'll show you a lot of things about the history, the structure, the mechanisms, the programming, things you really will find to be much more fascinating than you thought. And if you think about it as a technical subject, by the time we're finished with this course, you might think of it actually as an art form you would like to indulge in. Also, every weekday at 6 p.m. Eastern Standard Time, we have the Randomizer, where we randomly pull a term out of our technical hat, and we talk about that term in enough detail to gain a basic understanding of what it means. So the Randomizer is one of those things where you can join us live with your questions, comments, or ideas on the show, and we'll air you there and we'll see what you have to say and we'll give you the best answers we can. We hope you enjoy the Randomizer episodes, and I know we really enjoy the people who support our efforts to make this happen. So let's get on to autoionization. Now this sounds like something that strange compounds might do. They've got a couple of molecules floating around in there, and suddenly they exchange some particles or something and become slightly different molecules, but imbalanced, ionized. So first of all, we need to know what an ion is. The simplest way of explaining it is a basic molecule is neutral. It has the exact same number of protons and neutrons. Protons and electrons. Scratch that neutron remark. Don't know where that came from. The same number of protons and electrons, so they balance the charges to zero. So for most molecules, this is going to be the case. An unionized molecule has a net charge of zero. In reality, we often find that we need a compound to have some spurious behavior. We don't want it to be neat, unstimulated, and unchanging. We need it to have a form that will easily interact with other materials. In semiconductors, we often use, for instance, silicon as the basis of the atom for the crystals that we grow. Well, silicon has some interesting properties, and one of them is silicon atoms have exactly 4 electrons ready to bond with other atoms, just like carbon. One of the differences here is silicon tends to be a crystalline material and doesn't seem to do a lot chemically unless the right circumstances are reached. Now, silicon atoms together make this perfect matrix in which all the charges seem to be balanced and ready to move at the drop of a hat. However, what will happen in some cases is we find the energy to move those atoms around, those electrons around, isn't quite what we're looking for. So we'll come up with fake compounds that act like they have 4 electrons per atom. One way of doing that is to mix compounds with 3 electrons and compounds with 5 electrons. The most commonly known compound of that sort in the semiconductor world is probably gallium arsenide. This is known as a 3-5 semiconductor because by adding an element with 3 free electrons and one with 5 free electrons and putting together in a perfect crystal, you end up with 4 and 4 all over again. But the potential for those electrons electrically is a little different from what it would be in silicon. So here we've created an imbalance. We want something to act like it's about to be ionized, or the electrons can move easily all the time. Now, normal compounds, as I'm mentioning, often are very stable and they don't seem to do very much. So you think, well, autoionization, that would be something that would be kind of rare, wouldn't it? Well, autoionization is when the compound itself automatically, or for no particular reason other than it has random molecular motion, will become ionized. So instead of having, let's say, two molecules of the same thing, a proton will shift over to the other one and it'll gain a plus charge and the remaining fragment will gain a minus charge. So now we have ionized fragments floating around in the solution. Now what kind of weird molecule would do this? Oh, water. Water does this all the time. We often mention that water is a great solvent. It's a polar solvent, it's a polar molecule. And what does that really mean? Well, one of the things that you're probably not aware of is this. All of the water that we run into in nature typically has come from a well or underground or something, and it has a lot of minerals dissolved in it. How do the minerals like silicon and aluminum oxides and things and carbonates, how do those things dissolve in something as innocuous as water? It actually turns out that distilled deionized water is one of the most amazing solvents there is. Water, the basis of life, actually has the capacity to ionize itself and interact with every sort of molecule you can imagine. Well, setting oils aside, being a polar solution, which really means the molecule itself has a plus polarized end and a minus polarized end, and it's easily joined to other molecules. Water does something very interesting as a solvent. Let's say we put some salt crystals in the water. Now, salt, as we know it, table salt, is made of sodium, which is an extremely explosive and reactive metal, and chlorine, which is an extremely reactive and toxic gas, two deadly toxins. Combine them together and you get table salt, sodium chloride, which you can eat. It's kind of an odd thought that two deadly toxic materials can come together to make something you sprinkle on your fried egg in the morning. But it's just one of those natural things that happens. But why does sodium chloride dissolve so readily in water? Because water, instead of just H2O and H2O, does this interesting autoionization trick. What will happen is one of the hydrogen atoms bound to one of the water molecules will switch over and join to the other molecule, but not the whole molecule, not the whole atom, only the proton, the center of that atom. So you end up with an H3O, which has 3 hydrogens and a plus charge, and that's called the hydronium ion, and a hydroxyl, which is just OH with a minus. So it's not H2O and H2O anymore. Some pairs of water molecules in the liquid will switch into hydronium and hydroxyl. In this state, they're much more capable of reacting with other compounds, particularly those as salts that are ionic. So an ionic compound suddenly finds itself in the situation where, out of the population of water molecules, a significant number of them have just randomly transformed into ions themselves, and they will attach to the sodium and the chlorine atoms individually. When salt dissolves in water, there are not salt molecules floating around in the solution. They don't exist anymore. The salt is literally taken apart into its atoms, ions, and joined to the hydronium and the hydroxyl. Now, they are transported in solution, and this is what brine is. So a number of salts will undergo this process in liquid water because water automatically splits into these two rogue forms, these ionized forms, a plus ion and a minus ion. Is this the only compound that does it? Absolutely not. Ammonia will do it as well. Now, for anyone who knows some chemistry, ammonia is NH3. That's an ammonia atom with 3 hydrogens stuck on in a little triangle. And the ammonia atom, or molecule, I'm sorry, is a very good solvent for oils. Ammonia works kind of like the same process we just talked about. You have an NH3 here and an NH4 there, and one proton will switch over here, and you get an NH4 positive ion, which is called an anion. I'm sorry, a cation. I got it backwards. That happens sometimes. And you have an NH2, which is the minus, the cation. Now, if you look at a battery or you look at a capacitor, you will see a term anode and cathode, or you'll see that on a diode, an anode and a cathode. So what are those? Those are the electrical terminals that show you which terminal is positive, the anode is positive, and which one is negative, the cathode is negative. So when you look at ions, the same terminology holds. An anion is positive, and a cation or a cation is negative. So now you have the source, the etymology of the terms dividing cathode and anode and the two types of ions you're going to encounter. So the name makes sense. With ions in ammonia, it becomes more capable of dissolving things such as oils, fats, rubber. In fact, in times past, the only known way easily to dissolve latex was in ammonia. And normally when you buy liquid latex to put on something, you smell that sharp ammonia smell. That's because the ammonia is the solvent that keeps it in the liquid state. But as soon as you paint it on something and the ammonia evaporates away, which it readily does, the rubber solidifies. So latex can be put on, and that smell of ammonia is the solvent that keeps latex in a liquid state, being evaporated away. There are many other compounds that can do this as well. In fact, there is even an animal in nature, Architeuthis, the giant squid, which has so much ammonia in its flesh that it is inedible. It makes your eyes water, and it would probably make you extremely ill to try to eat it, which raises some interesting questions. Because ammonia is such a strong solvent of oils, it usually is very effective in breaking down the membranes of many cells. But when we see any sort of an organism like a giant squid, which can live with that much ammonia in its tissue, it begs the question, is it possible in other foreign seas and other worlds that there might be organisms living in a high ammonia environment that would probably kill most life on Earth? And it seems quite likely at this point, because we see examples of things on Earth that can live with those levels of ammonia. Another compound that will do this autoionization trick is sulfuric acid, but a lot of people don't mess with that. Now, it's commonly available in old style lead acid automobile batteries, and it's an actually old, very robust technology, but one that's well known. Sulfuric acid converts into a plus and a minus ion as well, as does hydrogen fluoride. One of the most aggressive acids you would think would be one that would eat glass, but that's not actually the case. Hydrogen sulfide is not a very powerful acid. Hydrogen fluoride. Let me say that properly. Hydrofluoric acid is what you get when you mix water and hydrogen fluoride. Hydrogen fluoride going into solution makes hydrofluoric acid. Hydrofluoric acid is a really nasty material, and it's because it has the ability to bond into things that you normally wouldn't think an acid would attach directly to. If you put hydrogen fluoride in contact with glass, it will literally etch the glass. So you have to store it in a different sort of a container. In fact, there are some things that are so dangerous you have to store them under other solutions to keep atmospheric air from reaching them because they have the ability to spontaneously react very quickly. If you had metallic sodium, for instance, which I said was a very explosive and reactive material, it is a metal. If you have metallic sodium, you often will store it under kerosene. Now, this seems counterintuitive because if you put sodium in water, it'll burst into flames, it'll make hydrogen, it'll explode. But if you put it under kerosene, which is a flammable liquid, it will not. This is because kerosene is a saturated hydrocarbon and is not very reactive the way water is. Water can split itself into hydrogen and oxygen. The oxygen heats up the material when it reacts with it, and the hydrogen ignites and it causes this horrible explosion and fire. So metallic sodium is pretty nasty stuff. You never put it in water, but to keep it from burning, you put it under kerosene. It seems completely the opposite of what you would expect. And yes, it's true that there are many chemicals that do things like that. For hydrogen fluoride, one of the worst things to remember is this. It's often used for cleaning certain materials, but if you get it on your skin, you won't feel it burn, but it will migrate into your tissue until it reaches your bones and it will attack the calcium in your bones. Really, really nasty, horribly painful. So stay away from hydrofluoric acid. Never store it in glass. In fact, just stay away from it. Well, autoionization. And I know if you're not a fan of chemistry, this is something you'll probably never run across, but it is an interesting subject. Autoionization is also, as it turns out, essential to the process of life. Because water is such a common and yet so unusual in so many ways compound, it's amazing that life exists the way it does at all. Think about the things that are different about water. When it freezes, it gets less dense. It fluffs up and floats, thus ice. There are only about 5 compounds that actually do that when they freeze or solidify. It's amazing. Autoionizing, solvent for almost anything, expands when it freezes, and yet it's not poisonous. We have to drink it every day. So, autoionization. Now, if anybody has any questions about autoionization, organic chemistry, things like that in general, the floor is open. Meanwhile, I'm going to encourage you to go to universeciencecenter.com or schultzlaboratories.com and to sign up as a member and support our efforts to grow and to add more material and to produce more shows like the Randomizer. And if you have the desire to talk with us directly, join us at 6 p.m. Eastern Standard Time on weekdays on the Randomizer, and we'll entertain your questions live on the air. Well, if anybody has any questions and I don't see anything coming in, I will go ahead and read my quote for the day. And it is, "My son, if your heart is wise, my heart will rejoice. Indeed, I myself." And that's Proverbs 23:15. Think about it. If you have a child, if you have a son, and he shows a little temperance and information in that head and wisdom, the ability to make the right choices, it will make you happy. You probably don't have to worry about him much. And what can be a better feeling than thinking that your kids are able to take care of themselves properly in this world? That's a great consolation to those people who have that wonderful gift. Well, since nothing more is happening on the question and answer forum, I think this is a success. And I hope you learned something new about chemistry and autoionization and polarity of diodes. And I hope that you have a wonderful evening. And I am Charles Schultz with the Randomizer, and make the world a better place. Thank you.